prevent Rice's theorem from working. B is the first of those, actually. And it's the one that says it's a trivial property. So the one that says I want the index for functions such that there's some other function. So it's got a different index, but it turns out it has the exact same mapping from input to output. Well, every function has that. Because all I have to do is you give me a function, and I'll give you one. I'll take your function, I'll take it f of x, and I'll do f of x minus f of x plus f of x. Okay. What's that give me? F of x. But is it a different implementation? Yeah, it involved two more computations, a minus and a plus associated. Or how about f of x plus 0? Same thing. If f of x diverges, f of x plus 0 diverges. If f of x converges, f of x plus 0 gives you the exact same value. So all functions have doppelgangers or imposters associated with them. So that particular one is trivial, and so that means you cannot apply Rice's theorem to it. The other one is if it's not an input-output behavior, and the one that says that it converges in no fewer steps than the input it's given, or something related to the length of the input. So what it does is it is the thing in no fewer than that, so it's at least linear. Okay. It says no fewer than, but it could be quadratic, it could be exponential, it could be super exponential, anything above that. What this is saying is I can write you can give me a function that runs in constant time, and I can give you back a function that does what yours does, and it takes exponential time to do it. What do? Well, just for fun, I take your input and I compute 2 to the value of your input. And then I throw it away. And then I do whatever it was you were doing. And so now I've taken exponential time to do what you did perhaps in constant time. But they both have the same input-output behavior. So anything that relates to performance, Rice's theorem has nothing to say about that particular property. Okay. Yes, sir?
Could you explain the notation for Z prime or Z apostrophe? What is it? LRR?
Oh, do you remember the notation I used earlier where what left does is the L, that's sort of the scripted one, takes, so we always start computation immediately to the right of our input with our Turing machine. And then what the L, that's the scripted L, does is it moves to the first 0. So it walks across the entire input. The R says, I'm going to go back across that till I get to the 0 I used to be at. How much time does it take to do that? Yeah. And then I finally decide I'm going to compute the value. So I could do 0 in constant time, or I could do it in linear time. Okay. So what this is showing, that's just an example of it. But you don't have to give me Turing machines for it. It's just, I did that so you would have a physical model that if that's the way you like to view things, with the operation of a physical model, then I can give you an example of that. Turing machine runs across the input, which takes it at least order the length of the input. Then it runs back across it. Well, that's 2 times the length of the input, big deal, plus 1. And we used to do it in 1, which is sublinear, right? And now we're at least linear in terms of doing it. This is the giveaway. I have designed the final to have giveaways in it. Please take advantage of those giveaways. Don't screw those ones up. And so one of the things and I don't expect you to be able to draw straight lines. I can't draw straight lines. So I will set up a problem. I'll have some number of clauses. They will all be 3 sat clauses, so they will have three terms in them. The terms can involve repeats, that's a possibility. And what you have to do is just, I'll give you everything that is to the left of that right column, those right columns associated with the clauses. How hard is it? Well, that's got A in it, this one, so I think I better put an 1 over here. This one, do I have a not A? No, nobody's got that. Oh, do I have a B? And if you put a 1 in there, that's okay. If you put a 2 in there, that's okay. But if you put a 2 in there, and I ask you to show me the solution, 1 second, David, then you're gonna have to give me one more line than you would have had to give me if you put 2 in there.
Do we have to put the zeros or can we just leave it blank?
No, you gotta put the zeros in if I don't put them in on this. And I promise you, I'm gonna put all the zeros in over here. I'm not gonna leave it the way I did it on that overhead where I had them blanked on that. I will fill all the zeros in, so if I can do it, you can do it. Okay, yeah. So I'd have to put a 0 over here, so the default is always 0. And then, of course, for C, this one's gonna be a 1, that's a 0. For not C, that'll be a 0, that's a 1. And good Lord, these are so obvious. For every clause, you have to have 2. Damn it. I am gonna go down at some point here. For each clause, there's going to be 2 of these fillers. So this has got 2 clauses. If you had 3 clauses, you'd have to have 3 fillers, and there would be 2 of each filler. But you have to have 3 pairs of fillers for that. And what happens is, if you look at this, if I try to figure out, I'm in great shape here. Why? Because with this one, I could choose this row, and this row. But I'd be in trouble. Why? If I chose these 3 rows, A, B, C. No, not A, B, C. A, not B, C. It would be wonderful for the first clause, it would be satisfied, but what about the second clause? It wouldn't be. So A, B, C would work. If I chose that, then this would have A and C, so it would have 2 of them. And this, if you did that way, it would have a 2 as well. And then how many fillers would you need? 1 for each of them. But if you write a 1 in here, then how many fillers are you gonna need for that one? 2 of them. It's up to you.
Why is that? Why do you need 2 fillers for it? Sorry.
Because the sum always has to be 3. See, this is your goal down here. 1, 1, 1. What the 1s here mean is I must choose A or not A. I must choose B or not B. I must choose C or not C. And then here, what I have to do is I have to get a 3 for each clause, and I only have 2 fillers. So that means at least one of the variables in that clause, that row has to have been chosen. That's the idea behind this one. Now, if I try to choose A or C and not C, I'm in deep trouble. Why? If I try to choose these 2 rows as part of my solution, this will sum to 2. Times sum to 2. So those ones force me to have, but there's no requirement on this one. They don't conflict with each other, the fillers, but you don't want to choose too many fillers because then you'll exceed the value 3, which is the value you're going for. Any other question on how to do that? Yes?
How would you go about converting that matrix to like the sequence of integers? And
Oh, this is the number 10010.
Oh, so that's binary?
No, it's decimal. So it's 10,010.
Oh, okay. And then
Okay,
like,
my
you're
goal
down to
is to achieve 11,133. Read this as decimal, they're not binary. The reason they're not binary is 3 is not a very good binary number. So, now you never get above 3, so I guess you could say that I'm doing it in base 4,
I
but
think you could
we
get
think of it as
5
base 10. Huh?
with your fillers. Like,
Pardon me?
You could get 5. If you
Oh, I could get too large a number, you're absolutely right, so to avoid that, yeah. Yeah, so the idea here though is treat them as decimal numbers. And just write down, this is 10,010, that is 10,000 if you chose that. So if I asked you to give me a solution to it as a set of numbers, and this one I could choose A, B, C. And then what I'd have to do is write down those numbers plus whatever fillers I needed to do that. And it better sum up to 11,133. Now, I'm not going to guarantee you that we're going to have only 3 variables. I'm not going to guarantee you that we're only going to have 2 clauses. There could be more variables. There could be more clauses. I suppose there could be fewer clauses, but that's bloody unlikely that I do 1 clause. Okay. Yes?
Will we have to be able to convert from SAT to FreeSat? Or are you just gonna make FreeSat?
You need to know how to do that. I will not do that to you on a problem like this, but I could ask you a question about that. It would be a separate question if I do that. Because this starts by assuming 3SAT is NP complete. And so I would have you start at the point where that particular group goes. I've told you this before, you need to know the gadgets associated with just the problems that we looked at, and what's the most complex gadget that we have. I mean, they get much more complex than what I've shown you. And the most complex, it's some 3 coloring, and it's the OR gadget. The OR gadget, you have to look at, and remember, the 3 colors are true, false, and base are the 3 colors associated with it. Which if you want, there could be green, red, and yellow, whatever you want those to be, but they're typically, the reason they do TF and base is T and F are what a variable is forced to, and remember the whole structure is designed just like this little one guarantees that you cannot choose it to minimize. This is the one from vertex covering. And vertex covering, what you have, do you remember what the rest of it is, how you use these gadgets? The first one is the gadget you're trying to basically minimize, and even though the problem is not presented as a minimization problem, you're given a value that is the minimum possible that you could ever do with this. And the value is the number of variables plus 2 times the number of clauses. And the reason that's optimal is you've got to choose one of these variables up here to cover the edge between those 2, the variable and not the variable. So you got that as a minimum, 1 per variable, and you have to choose 2 edges here to, 2 nodes here to cover the 3 edges there. So that's the absolute minimum. And then what happens is you add a bunch of other edges. The edges are, if this happens to be variable V, then there'll be an edge from there to there. If this happens to be variable not V, there'll be an edge from there down to there. And those edges, if I chose V, then V would be cut, this edge would be covered. And I would not have to choose this particular node. And then what I would do is to choose these 2. And if I had something really bizarre like V or not V in here, which is possible, right? I could have a clause like that. By choosing this one, it would cover the edge that comes down there. Now, more typically what's going to happen is all the variables in there are going to be unique, and they're either going to be complemented or not complemented. And so there's going to be an edge from 3 different pairs except that might not happen. Why? Because I might have one of these that's like B or A. Now what happens in that circumstance? Let's assume that's B. There would be an edge here and an edge there, and if I had A over here, there would be an edge coming down there. If I chose A, then I wouldn't have to choose this. If I chose B, I wouldn't have to choose either of these, so what would I choose? Any three I want to, any two out of three I want to. When's the only time I'm forced in my choices? If I have, let's say, this is A, and up here, I chose not A. So I have an edge into there, and I chose not A. So I don't know how to show that to you, but let me call this A. So that's coming around here, and it turns out I didn't choose A. I chose not A. So the edge here is not covered. So what do I have to do? I must choose this node to cover it. When's the only time I fail? But I absolutely cannot choose nodes here to meet the minimum requirement. Let's say that's A, B, and C, and I didn't choose, I chose not A, not B, not C. What's going to happen? I have three edges coming into this thing. One from A, one from B, one from C. Not a single one of those edges is covered. What would I have to do? I'd have to choose all three of these to cover the edges coming in. Now I've broken the optimization criteria. But what did that mean? That meant that assignment of values to the variables did not satisfy this clause. And if there is no way to satisfy all the clauses that I have, then I'm absolutely guaranteed that I will not meet the minimum requirement. So give me a Boolean expression that is not satisfiable. Give me one. Easy one.
Not A, not B, not C.
No. How about A or A or A, one clause. Not A or not A or not A, second clause. How many clauses can you satisfy there?
One.
That's right. Okay, so what'll happen is if you choose A, then you'll be able to minimize the number of nodes that you choose out of this gadget here that has A. But the one that's not A, not A, not A, you'll have to choose all three of these to cover the edges coming into it.
What constitutes covering an edge?
It means that one of the nodes at one end of the edge is chosen.
Okay.
Okay.
So either
So-
one can be chosen, and then that edge is covered.
Right. So I have, the only way I could possibly cover that thing, I wish I'd brought up. I didn't realize I would get one of these wonderful white, but does anybody have a marker that I could just steal from you? Borrow. That's a marker, all right, a whole collection of them. Okay. So if I had that circumstance, what would happen is I've got A, not A, that gadget. Then I would have two gadgets, A, not A, not A, not A.
So it's one gadget for every clause?
That is a gadget for every clause.
Okay.
And it has all of the labels that are associated with the variables or the complement to the variable that appears. So this is the one that basically is and not A. A and not A. Now you know that's not satisfiable.
Right.
Okay. So the only way I can handle this, because it's got an edge into there and an edge into here, for all of those, there are two ways I can do it. If I choose this one, so let's say I choose this one, then I still have to choose two of these to cover the internal edges. So I could choose any two, like those two. That'll work. The problem is, now this is covered because I chose A. This is covered, and that's covered because I chose A. And now because I chose these two, all three of these are covered. Yes, sir?
So the gadget goes from the variable to other instances of the variable, or does it go from the variable to the instance of the negation of the variable?
No, it goes, this is, we're doing the vertex cover.
Yeah.
In that case, you have the variable gadget, and the variable gadget draws lines every place that variable appears. It either, if it's A, then every place A appears, there's an edge to A in the clause gadget.
Okay, I just thought it was the other way around. My bad.
Oh, it can go either direction because they're undirected.
No, I mean like,
I-
not A goes to the A's in the
Oh,
first
no,
sentence.
you know what you're thinking of? You're thinking of independent set.
Okay.
Independent set, you create clause gadgets, and then if you have A in a clause here and you have not A in a clause over here, you connect them together.
Okay.
That's independent set.
So in the case of the vertex covering problem, you go from the instance of the variable in the variable gadget down to the clause.
Right,
instance.
right. Okay. So now the problem is here, since that's not chosen, I haven't managed to cover any of these edges here. If I try to choose two of these, that will cover this, and this, and that will be uncovered. So I have to choose this one as well, and I won't meet my goal, which my goal was 1 plus 4. 1, the number of variable gadgets, plus twice the number of clause gadgets. Yes, sir?
What does that actually mean, the 1 plus 4? Like,
It's number of variables, which is the number of variable gadgets,
right.
plus twice the number of clauses.
And you have to choose that many edges
I choose that many nodes.
within the bottom two.
No, I have to choose that many nodes to cover every single edge.
Okay, and if you can't do it in that many,
Then it means that the original expression is unsatisfiable.
okay,
But if I can do it, the expression is satisfiable.
gotcha.
Okay. So this one's unsatisfiable because it's actually going to take me 1, 2, 3, 4, 5, 6, and that doesn't reach my goal of 5.
Okay.
Okay. Now, there was another way to handle all the edges. I could have decided to choose A and not A. I could have. That would have double covered this one. It would have taken care of all of these. And now I would only need 2 of these. But what's the problem with that? That would still be 6. Because it would be 2 plus 2 plus 2.
Right.
So there's no way I can achieve that in this case because I have a self-contradictory expression. Contradicts itself, and so you can't do it. But if there is an assignment, you can achieve it because you choose either a variable or its complement, so that's the number of variables, and you choose only 2 nodes within a clause, which you know is the minimum, just that's what it takes to cover the internal ones, and that's saying that at least one of these edges coming in was already taken care of, so I didn't need to choose that particular node in order to cover that one.
I don't know, waste time, but do you mind showing one that works with?
Sure.
variables?
Sure, let's make this,
You got an eraser.
I'm gone, I'm back. Okay. So let's assume I've got 2 variables, B, not B, up here, And now what I do is I'll change this to, I'll make it A, B, B, and this one over here, I'll make it not A. I gotta get rid of all of those checks. I'll make it not A, not B, and how about not B again? So this could be satisfied in a number of different ways, but one way to do it is I might choose A and I might choose not B to satisfy this. Okay. So if I do that, if I choose A, let me get that star off of that, then choosing A will cover this. Let's see, that's an A, this is a B, good grief, okay. So that edge is gone. This is not A, goes to there, and not B goes to here. Okay, so that covers that. So I choose this one. It covers those two edges, but it doesn't, let's say did I choose B in here? That's a B. So that means its edge is this one. I apologize, they're not, I needed to grab a different one of these markers. That one is dying on you, David.
Blue's my favorite color.
Blue's your favorite color, that explains it. Okay. Love it. Okay, that's a B, this is the not B. Okay. This is not B over to here. So I choose, let's say, A and not B. So A covers those two edges. So what I have to do is I must choose that one, and I can choose either of these others and cover the internal edges in there. Because choosing this is only going to take care of those two, and that one won't be taken care of. So I can choose either one of these. Let's just assume I choose this one, and that's going to cover that. And then this was, yeah, that was an A as well. Sorry about that. Okay. So it's A or B, and this one was not A or not B or not B, because I didn't feel like going out to C, if you don't mind. Okay. So now in this particular case, that edge is covered and that edge is covered. This edge is not covered, so I must choose this one, and then I can choose either of these two to finish it. So let me just choose that, and that'll cover all of the internal edges of that. So that one works. And the idea behind it is at least one of the incoming edges gets handled automatically for you, because that variable or the complement of that variable has been chosen. Now, if more than one of those gets covered, you have choice. But let's say it only takes care of only one of the literals in that clause is actually true, and the other two are false, then you must choose those other two. Okay?
Did you get the big one from B to B over there?
This one here, this one I got,
You chose, because you chose.
because I chose here.
I see, okay.
Yeah, that's how I got that one. Yeah, so that's the check there. Okay?
Thank you.
Okay. Any other questions on it? Yes.
Whenever you're computing the amount of nodes that you need to choose in order to cover everything, do you count A and not A, like, together? as
No, you
separate
just
variables?
count the number, yes, you count them together, just the number of variables.
So
Now,
A and B.
yeah, A, not A is one variable. The variable is A, and it either can appear uncomplemented or complemented.
Okay.
Okay. Okay, another giveaway. I want a couple of, there's actually even more giveaways than this that are on it. This one is one where you're just doing what's called first fit or list scheduling. You're given a list, and what you have to do is always choose, you gotta follow the order of that list and always choose the processor that is free at that time. Now, if both processors are free, you pick the first one. So at the very beginning, I pick processor 1 and I put T1 on it. I cannot wait to do T2, so I put it on processor 2. Processor 1 finishes first, so I do T3 on it. Processor 1 is still free. First one, it's free at time 4, and so I put T4 on that, which runs length 4. And then so on down the line. You can follow that schedule. First fit is one strategy which just does lists. I don't expect you to remember this, but it does pretty well. Even though it's a junky schedule, things never get worse, even in the limit, than being twice as bad as the best schedule, which is not so bad. Do you know why? Logically, why is that true? That you'll never be worse than twice as bad?
Because there's no downtime. Both
Yeah,
processes
the other thing
are
is you can ignore the second processor. Just totally ignore it. And schedule the whole thing on one processor, and that'll be no worse than, so that's the limiting case. But it turns out you do much better, and statistically, empirically, you do much better than that. But the better strategy is the one, or I don't have it here, is if you sort them longest to shortest, which is called critical path. If you ever take courses in business colleges, they always like to teach you about CPT, which is this critical time scheduling process, which is the idea that if you're trying to get tasks done, take the hardest one and do it first. Get that one done first, and then what happens in that is you're making room for things, and you're not going to get in this